So we've been looking at network exchange experiments, where remember we have nodes who are occupied by people, connected by edges to others that they can have an exchange with. And exchanges generate some benefit that these two people share. What we're interested in doing is figuring out how the structure of the network affects who gets what, who has power. We've seen in experiments various things that can happen. What we want to do now is begin to build a theory that we can use both to explain what happened in those experiments and to predict what would happen on other more complicated networks. And our theory is going to have essentially two pieces to it. The first is stability, and the second is going to be Nash bargaining outcomes. But let's first begin with talking about what we mean by an outcome in the first place. An outcome consists of two things. First, it's a matching in our network in which each node is part of at most one edge. That's reflecting the one exchange rule. You can only be partners or best friends with one other person. Second, the outcome has to describe the values. Who gets what in every exchange? And of course, since we have the exchanges producing a value of 1, the sum of node values on edges in the matching has to be just 1. And any node not in the matching is locked out and they get 0. The question is, what do we expect the outcomes to look like? And we're going to have a couple of basic principles here. The first one is that we would not expect any outcome to be unstable. An unstable outcome is one where any pair of nodes connected by an edge have values that sum to less than 1. The reason for this is, suppose you've got two nodes connected by an edge and their values sum to less than 1. Well, then they're not exchanging with each other. But if they did, they could have at least 1, or they could have exactly 1, and that's better than what they're getting now. So you would expect them to defect from their current partners and join up and split the 1 they can have. That shouldn't happen. Anything like that is unstable. What we expect to see instead are stable outcomes, one where there is no instability. Let's look at some examples of stable outcomes. In the 3-node path, it's really simple. There's one and only one stable outcome, and that's the one in which the node B in the middle of the path gets everything. They get a value 1, and nodes A and C on the ends get 0. Clearly, B is in a more powerful position than A and C, and this is the only outcome that's stable. Because if B exchanges with C, and in that exchange, B is going to get less than 1, then A and B are connected by an edge, and the sum of their values is less than 1. It's B's value plus 0 for A. So you would expect A and B to pair up and do something that is better, presumably for B. But in other networks, there are lots of stable outcomes. The simplest example of that is a 2-node path with just A and B. In fact, any way A and B split up their surplus of 1 is going to be a stable outcome because there are no alternative partners. If that was the only issue, it wouldn't be much of a problem, but in fact it's not. Look at the 4-node path here, A, B, C, and D. We expect the exchanges to be between A and B and C and D, and that edge between B and C to be unused. But let's look at some stable outcomes. One outcome that's stable is every node getting a half. And that's pretty easy to see because the only unused edge is the BC edge, and B and C's values sum to exactly 1. Another stable outcome is where the two nodes in the middle, B and C, get 2/3 each, and the nodes on the end each get 1/3. That too is stable, and that one looks more plausible than the first one. In the first one, where everybody gets a half, B and C have the same power as A and D. And that seems implausible because B and C are clearly in a better position than are A and D. B and C have each other as potential partners, where A and D have no potential partners other than A for B and C for D. So what's wrong here? Well, the problem is the way the surplus is being split in those exchanges isn't reasonable. We're going to need a little more theory to talk about how that might occur. And let's start building that theory. Let's do it with just 2 nodes first. Let's think about A and B. Suppose if A and B form a deal, they get a surplus of T. That's, in our experience, has always been 1, but it could be anything. The key here is we're going to add another element. We're going to give A and B outside options, X for A and Y for B. This is what the 2 nodes get if they don't reach a deal. So if A and B reach a deal, they get T to share. If they don't reach a deal, they each get their outside options and they don't get T to share. The question is, how do the outside options affect what happens in their deal? John Nash, the same John Nash we talked about with game theory, has a nice theory about this. His prediction is what we call a Nash bargaining outcome. The first and really obvious aspect is that if the sum of the outside options, x and y, is bigger than t, then A and B are not going to reach an agreement. They'd be better off to go their own ways and get their outside options. But if the sum of their outside options is less than t, then there's a reason to reach a deal. They can have more. They can split that difference that they have. And the question is, how do they split it? So let's define the surplus from their deal to be t minus the sum of their outside options. That's how much extra they get together from reaching a deal over what they would have had on their outside options. Nash's solution is that we would expect the two of them to split the surplus equally. So we would expect node A to get the value of his outside option x plus s over 2, half the surplus, and node B to get the value of his outside option plus s over 2. That's the Nash bargaining outcome. So what we're going to do is take that Nash bargaining outcome and take it back to our networks and use it to predict what would happen. Let's go back to the 4-node path where everybody was getting a half, and A and B are exchanging, and C and D are exchanging. And we argued that that doesn't seem reasonable because B is not getting enough. Let's use Nash's idea to figure out why not. So let's focus just on AB. A's outside option in the AB negotiation is 0. It's got no place else to go. B has an outside option, though. That's to deal with C. And the value of B's outside option is what C has to have, which is a half, the difference between that and 1, what B and C could get if they join up. So the value of B's outside option is 1 minus the half C gets, or just 1/2. The surplus then in the AB deal is the one they can have if they reach a deal minus the sum of their outside options, which add up to a half, and so their surplus is a half. Nash's idea is that surplus is going to be split equally. So node A should get the outside option of 0 plus half the surplus, or a fourth, and get just a fourth. B should get his outside option of a half plus half the surplus, another fourth, and that gives B 3/4. Okay, that's beginning to reflect now the idea that B's got more power than A. Here B gets 3/4 and A gets 1/4. So that says, well, the 1/2, 1/2, 1/2 prediction is not good. Let's try 1/4, 3/4, 1/2, 1/2. But clearly 1/2 for C isn't right either, because C is just like B, right? C has an alternative to dealing with D, it's B. So we need to figure out what C would get in the deal with D using C's outside option, which is B's value. Now as we begin to do this, notice that what's going to happen is that B's and C's outside options are tied together. They're, for each of them, 1 minus the other's value, and the other's value is changing every time we do this. So what we're eventually going to need is an equilibrium prediction, some way to predict what we would expect to happen when all of the outside options are figured correctly given the values in the exchanges. And that'll be our next topic.